Here again, let's talk about the full basic concept of mathematical language. And here's our the language of set, language of function, relation, and binary operation. First is set of language. Set theory is a branch of mathematics that studies sets or the mathematical science of infinite. It was introduced by George Cantor, a German mathematician, in 1870s. Set is defined as a well-defined collection of objects. These objects are called elements or the members of the set. There are two ways to represent this. First is roster method and rule method. Roster method is also known as or called as tabulation method. This is where the elements uh, or the set are enumerated and separated by a comma inside a bracket. For example, we have your open bracket 1, 2, 3, 4, which is separated by a comma. Second method is the rule method, and this is also known as or called as the builder notation. This symbol written as x such as p of x, which is wherein your x is the element. Okay. Then for example, x as such that x is a positive integer that is less than 5. We have different classifications of set. First is that finite set. It is a set whose elements are limited or countable that you can count. So for example, we have A. Uh, inside your brackets, we have 1, 2, 3. A unit set is a set that has only one element. This is also called a singleton. On the contrary, the unique set with no elements, this can be called as empty set or null set. It is denoted by this symbol, null set, or a bracket, a close and open bracket with nothing inside your bracket. That is an empty set. An example of this, okay, so for example of unit set. Let's have n is equals to x such that x is a whole number which is greater than 1 but less than 3, in which is n, uh, what do you call this, in roster method, which is can be expressed as or answered as your n is simply equals to 2. Another example, we have for empty set. Let's have I, which is this is a set of I, which is your x, such as x, which is your element, is an integer less than 2, but greater than 1. So that is then, take note class, okay? Your x is an integer that is less than 2, but greater than 1, wherein you can find any integers between 1 and 2. So that is then 0 or nothing. So then you may just simply, your set I here is null or this symbol. Next is universal set. Universal set contains all the sets under investigation that is denoted by capital U. Example of this, we have U, okay, wherein your x element, such as x is a positive integers, that is x to the power 2 is equals to 4. And you can have any variables you're going to replace, okay, your x, okay, at such that this is equal to 4. Then another set of your another example of universal set, which is okay, this one, this is right in roster method. We have 1, 2, 3, 4, 5, 6, 7, 8. So for example, if you're going to write this in rule method, okay, this will be such that x as such that x are all uh, positive integers that is less than 10. So then in roster method, this will be u, okay, open parenthesis 1, 2, 3, 4, 5, 6, 7, only up to 9 that is less than 10. Okay. And another, okay, we have here, say for example, okay, universal set, or you have, sorry for this, this should be u, universal set wherein your x is such that x is an animal that wherein you can find it in Manila Zoo. Which is, okay, your elements here, okay, it can be a list of animals that you can find in Manila Zoo. Next is the cardinal number. Cardinal number. A cardinal number is the number of elements or members in the set, okay, in which is you can count it how many elements inside in a set. This is denoted by small n here, okay, an italic n. Then you have your set, okay, object or set. It could be a letter or like a, okay, wherein your a is a set. Say for example, what is the cardinality of a set? C. Okay, wherein your x or element is such that your x is a set of vowel letters. You know how many vowel letters are? We only have, okay, a, e, e, o, u. Okay, that is we can count it 1, 2, 3, 4, 5. So then the cardinality of the sets of vowel letters are just simply is equals to 5. Okay, there is also a subset. Okay, a subset is symbolized like this. Okay, this is wherein if A and B, okay, are sets, okay, which is also A is called a subset of B when also this is written as A, okay, this symbol, this subset, okay, your A is a subset of B if and only the elements of uh, the elements symbol, this one, this is your element symbol, the only element of A that is your A, which is also an element of your B. That means that all the elements that where can you find in your A, inside in your bracket A, okay, can be also present in your set B. Then you call that subset. There is also a proper subset. A proper subset is wherein, okay, take note of this, okay, symbol. There is no line below. So this is a proper subset. Okay, when written as A is a proper subset of B, if and only if every element, okay, the symbol is element A of A is in B, okay, that contains all the elements of your A in B. But there is at least, okay, one of the element in B that cannot be found in set A. Okay, that is a proper subset. That means all of the sets in your A can be found in set B. But otherwise, when you say B is a proper subset of A, that cannot be wrong. Okay, it could be. Okay, B is not a proper subset. Later on, we're going to talk about that. There is also a symbol for not proper subset. Okay, another again is we have a superset. A superset that is, okay, that has the same element, okay, as B. That means both of them, set A and set B, contains the same elements inside in your brackets. Then we call them superset. Okay, we also have a proper superset. A proper superset, there is no line below. Okay, same as a proper here, but inverse. Okay, to your A. That is where your A has, okay, your B's element and more, okay, such that your elements inside were answered. Say for example your elements are 1, 2, 3, 4, okay, that is a proper subset of your B, wherein your B here has 1, 2, 3. Then your A contains more than the elements of your B, then it can be called as a proper superset. Okay, so then just like what I told you earlier, okay, there is also not a superset. Okay, not a superset is just simply there is a like this symbol. Okay, the superset symbol, then there is a not. Okay, this one is not B. Okay, this is where your A is not a superset of B. Say for example, okay, this is your A that contains the element 1, 2, 3, 6, 1, 2, 6, which is not a superset of your uh, B, that is 1 in 9. Okay, for not subset or proper subset, okay, and not element, okay, these are the symbols. Okay, this one is the not proper subset. This is also not element. Okay, just for you to take note of those symbols. Another symbols, okay, just such as this one. Okay, these symbols are all brackets. Okay, it's just that, okay, different brackets. Okay, such as, okay, this bracket is parenthesis. Okay, or called round brackets. This one is also brackets, that is a box brackets or square bracket. This one is a brackets also, that is curly. Okay, or we call it braces. And this one, okay, the greater one, greater than and lesser than, this is called also as angle brackets. Next, we have union. Union is this symbol. Let's say let's use a set of A and B. Okay, in A or B or both. Okay, example. Let's say for example, your set A 1, 2, 3, and B is 3, 4, 5. Then, if the union of this is the combinations of all your elements, okay, of your both A and B, that is the union. Then you can say that your A union B is equals to contains all the elements of your A and all the elements of your set B. That is then 1, 2, 3, 4, 5, which is also they're both common in elements of 3. Next is the intersection. Intersection is the inverse, okay, U of your union. Okay, let's use the same set, A and B, for example. Okay, in both A and B, let's have an example that your A here has contains the elements of 2, 3, 4, 5, and your B has also 3 and 4. Okay, in which is the intersection that contains the same element which has both set has given. Okay, then you can say that your A here, okay, intersection with your B that is at your element 3 and 4 and 3 and 4. Next is the complement. Complement is simply as you have your A here and this one. Okay, this one is a null symbol. Okay, example, let A and B be a subset of universal set U, wherein your A is this one. You have contains the element of A, B, C, D, and E. And your universal set, okay, this one, your universal set here contains A, B, C, D, E, F, G. Okay, although your set A only contains A, B, C, D, and E. Okay, in which is we don't know how many sets inside in your universal set. It could be two or more. It could be there is a B or C or D, something like that. Okay, there could be a superset inside in your universal set. Okay, so then if we will just, okay, talking about the null set of your A set, so that is then that is not contained of your universal set. Okay, you're going to refer that on your universal set, in which is, okay, this one, your set A does not contain your element of F and G. So that is the complement. The complement of A is simply as your F and G in your one. Okay. Now let's identify now then if this set, okay, these sets are functions. Okay. To determine your a and b actually are functions, they're functions. Why? Because for each every values of your x here, okay, your x here contains only one value of your, okay, y, okay, which is your domain and your range, okay, that contains, you have 1 of your 3, 2 of your 4, 3 of your 5, 4 of your 6, okay. So then next we have your b. This is also, you have 1 to 7, 2 of 3, 0 of 1, 1 of 5, and 2 of 5. Take note class, although in your last two order pair here, you have your 1, 2, which only contains only on your y, that is just 1. But then we are talking about uh, when we say your first component, okay, that contains the same, okay, only 1 in your x, okay. Unlike in your c, you have your 3 here, it is only 1, okay. Then your relation c is not a function, okay. This is not a function. Why? Because the two ordered pair, okay, have the same x value. You have your x value here, okay. Yeah. The two ordered pair here for your y, okay, have the same value of your x. It should be your x has contained, okay, a value of your y, okay. It is not, okay, either the other side, the other way. Okay, clear? So next is the language of binary operation. So the study of algebraic structures that focuses on the investigations of set associated by a single operations that satisfy the certain reasonable actions. You know what our actions are, okay? This is the accepted truth, okay? Which is also, we're going to take note that a group here is a set of elements, okay? This is denoted by a capital G. This one, G, we have G here, G here, G here. Okay, that means this is a group set, okay? Group set. This is a group set, this is a group set, this is a group set, okay? Now, these are the binary operations that you should satisfy the four properties, okay? There are four properties, okay, of your binary operations. First is we have the closure property. The closure property is just simply as when your A here multiplied by your B is equals to C, okay, wherein, okay, all of this element is the element of your group set. Okay, for all of your elements A, B, and C, that is the element, okay, is the element, okay, of your group set. For associative property, you have here, okay, from our operations, okay, basic, okay, so this is just the same, okay, this is associative, okay, you have your association between A and B, okay, brackets, okay, times C, or this can be A, okay, multiplied by B, okay, open brackets and close, okay, you are now taking down to B and C, such that for all of your elements A, B, C, okay, is, okay, the elements in your group set. For your identity proper such that, okay, an element E in a group set such that for all of your A, okay, is an element on in a group set. Okay, this is just simply as your A times your element of your group set, or E is the element of your A. For inverse property, take note that this is just the same as in your inverse property of your multiplication. So for each and every A of an element in your group set, there is an element of your inverse A, or actually this can be a fraction of your 1 over A in your group set, such that your A then multiplied by A to the power of 1, okay, actually this will be cancelled out, remain as 1, okay, is that is just equal to 1, right? Okay, then reverse here on the other side, you have your A, Okay, negative 1 to the power of negative 1 multiplied by a, that is just simply equal to the element. Thank you.